Right, welcome back for round two. We're going to pick up where we left off and look at myopia. Now, on the next handout, figure 3, I'm going to title this myopia. Now, myopia just means short sight. I find these terms a little bit difficult, but they actually mean what they say. Short sight means you can see things at short distances. Say that again. It means you can see things at short distances. You can focus on things that are up close, but you can't focus on things that are far away. So short sight means you can focus nearby objects, but you cannot focus distant objects. So if you're short-sighted, it means you're good at short distances. Your problem is long distances. Now, what we're going to look at is how that actually works in the myopic eye. A myopic eye, a short-sighted eye, has trouble with distant objects. So let's put a distant object out in front of this eye. So the distant object is at infinity. Now that means that rays of light coming from that object are effectively parallel when they reach the eye. Now, the normal eye would simply relax and the lens would naturally focus those rays on the retina. But the myopic, the short-sighted eye doesn't do that. The problem with the myopic eye is that even when it's fully relaxed, the rays don't meet at the retina. What happens is that the rays are converged and that they meet a little bit short of the retina, say here. So you would have a focused image here. But that's no good because the retina is here. So what you actually get is a blurred or out of focus image at the retina. And when that image is sent back down the optic nerve to the brain can't interpret it and you perceive a blurred image. The reason for it is that nature has done you wrong and has given you an eyeball that is just a little bit too long for the lens that you've got. Okay, so evolution has designed us an eye where the eyeball is should be equal to the focal length of the lens, but in a short-sighted person it isn't. They get issued with eyeballs that are slightly too long, and therefore the image turns up here. Now, I think there are other causes of myopia as well, but that's one reason for it. Okay, so what have we got? We've got parallel rays coming from an object at infinity. The rays meet before the retina, and therefore we don't get a focused image, we get an unfocused image. So what's going on is that even when fully relaxed, the eye cannot focus. an image on the retina. And the reason is because the eyeball is too long. Now, back when we were all running around in tribes, that would have been a problem, I guess. And you would think that evolution would weed out short-sightedness and prefer normal vision, and I think it does. But what we find in modern society, at least, is that about 20%, about 1 in 5 of us, have either short sight or long sight. We have some sort of defect of vision which requires correction. And we have devised ways of doing that. And the ways are using glass spectacle lenses, a pair of glasses, or contact lenses which you actually put into your eye. And they both basically do the same thing, which is they bend the light to fix the problem, so that the action of the lens, coupled with the action of the eye, results in a focused image being formed on the retina. So, can you see, or can you think, what kind of a lens we need to move this image from here to here? Yeah, okay. Yes. Okay. So I'm going to jump to figure 5 actually. In my notes I used figure 4 to illustrate the near point, but I'm not going to do that because I think it's going to confuse the issue a little bit. So what we want to do is fix an object that's coming from infinity. The answer is that, as you can see here, this lens by itself is converging the rays here. So we don't want to converge them here, we want to converge them here. In fact, what we want to do is to converge them a little less than they actually are. So what we can do is, if we stick a diverging lens in front of the eye that diverges the rays slightly, then when they come to the converging lens of the eye and get converged, they will actually wind up on the retina. So let's just see how that's going to go. So we have rays that are coming from a distant object and that therefore parallel. I've gone a bit too far there. So if we put a diverging lens in front of the eyeball, like so. It's not a very good diverging lens. What will it do? Well, it'll diverge the rays of light. Now they might actually miss the lens here, but that doesn't matter because we're drawing schematically. So the rays get diverged a little bit. Okay, and then when they hit the converging lens, they get converged again, and the combination of divergence and convergence is going to mean that they finish up nicely converged like that on the retina. Okay. Yes. Okay. Now, if we do that, we're going to get a focused image on the retina. And we'll see that as a focused image, a clear, sharp image. Now, what has the diverging lens done here? Well, the diverging lens takes our parallel rays of light from infinity and it diverges them. Now, if you remember, what a diverging lens does is it diverges parallel rays of light and the point from which those rays appear to diverge is the focal point of the lens. So this will be the focal point of the lens. Right. So that's why I shouldn't have skipped diagram 4. Alright, we have to go back to diagram 4. Okay, so this is what actually happens then. Parallel rays from a distant object are diverged slightly, and then they're focused to arrive at the retina. Now, the uncorrected eye can't do that. It focuses parallel rays of light before the retina. But what we said was that short sight was the case where you can't focus distant objects, that's this case, but you can focus nearby objects. So if you push the object in from infinity towards the eye, then the eyeball is going to cause the image to move towards the retina. And the eyeball can also help that process because it can squeeze a bit in order to do that, but it doesn't need to. In fact, if it stays relaxed and doesn't change, then what you'll find is that at a particular distance, the focal length will be equal to, no, not focal length, the image distance will be equal to the length of the eyeball. In other words, if we push the object in, we'll get to some point, say here, where the rays are not parallel, but they're not quite, they're not parallel, but the eye lens is able to focus them on the back of the eye. Now, I haven't explained that at all well, but if you remember doing the experiment with the lens, when we formed objects and images, or images of a bright object, when we push the object in towards the lens, the image moves out. And that's what's happening here. As an object gets closer, or as the eye looks at objects closer to, the image is going to move further away. And at a certain distance, the fully relaxed eye, the object distance will be such that the image distance is equal to the length of the eyeball, and so we will get a focused image on the eyeball. Now, the distance at which that happens is the far point. So this is the actual far point of the myopic eye. Okay, so they like to be able to focus objects at a far point of infinity, but they can't. The actual far point is much closer to the myopic eye. Okay, so So then what the diverging lens is doing is it's diverging the rays of light. And if it diverges the rays of light and in such a way that, that's worked out quite nicely, if it's done it in such a way that the rays appear to be coming from the actual far point of the eye, then the eye says, oh, okay, then I can deal with those rays, and it will focus them on the retina, like so. Okay. And in that case, because this is a diverging lens, it's diverging parallel rays, and the point from which those rays come is the focal point. Of the diverging lens. So, therefore, the diverging lens that we need has to have a focal length which is equal to the far point distance of the actual eye. In other words, the far point of the eye is the same as the focal point of the diverging lens. So okay, so parallel rays diverge so that they appear to come from the actual far point of the eye. And therefore, the far point distance, the actual far point distance, is equal to the focal length that's required. Now, I said that was difficult. I made a bit of a meal of that, but you might need to go back and go over that bit again. That's the beauty of video. And if you've drawn these diagrams as you go along, and if you go over them, that may help. But it takes a few times, I think, to get your head around this. Okay. We're at 18 minutes. We're going to keep going. I'm going to turn over at this point, so hope you've got what you need from that, to diagram 6. Okay. Now diagram 6 then is going to be hypermetropia. Okay. Now, so myopia is short sight. Hypermetropia is so-called long sight. Now, if you want to deconstruct the name, I think the pia bit has to do with the eye and vision. The hyper, well, hyper I think means long. So think about if you get hyperextension, that's when a muscle or a tendon has been overextended. It's been made to go longer than it should have done. And you can be hyper or hypoglycemic if you're diabetic. And I think hypo is when you're low in blood sugar and hyper is when you're high. Or maybe it's the other way around. So the hyper refers to the long bit and the pia bit refers to the sight, I think. Now, so long sight, again, it means what it says. It means you can focus objects at a distance, so you can focus distant objects, but you cannot focus nearby objects. So in long sight, the long distances are not your problem. You can see things that are a long way away, but the problem is things that are nearby, things that you can't see. Now, typically, this is the kind of condition that arises in older people. So as you get older, you tend to find it more difficult to read things close up, and therefore older people quite often have to get reading glasses. Well, their problem is long sight. They can still focus perfectly well on things at a distance, but they can't focus on things that are close to them. So their nearby focus is going. And the reason for this, I think, well, again, there are a number of reasons for it, but one reason is that as you age, your ciliary muscles weaken a little bit, and the eye lens, the tissue gets a little bit stiffer. And there's a dog. Don't you dare do that in my garden. Oh, he did. He dropped one. Right. Yes. So the eye lens actually gets stiffer with age, and therefore, even when the ciliary muscle presses on it, it can't change shape as easily as it could, and therefore you can't accommodate nearby objects. Right, let's see if we can make this work. Now, my version of this diagram has a lot of correction on it, so this could be badly wrong. Okay. All right, well, let's see what the problem is. The problem is things that are up close. So if you have something that is quite close by, in fact, say it's at 25 centimeters. So an object at 25 centimeters. In other words, it's at a normal near point. So rays of light from such an object are diverging when they reach the eye. And what you want the eye to do is to focus them here. But in the long-sighted eye, the eye can't quite manage that. So it converges the rays a bit, but not enough for them to meet at the retina. And so they don't quite meet at the retina. They would meet somewhere beyond the retina here, but they don't. So what we get at the retina is a blurred image. Okay. So that means that, say you're holding a newspaper close to your eyes, 25 centimeters away, the text looks blurry. Okay, so what have we got going on here? So a nearby object in particular one at the normal near point of 25 centimeters cannot be focused. Because Okay, so the because is that the eye lens cannot be made sufficiently convex. The ciliary muscles can't squash and fatten the lens enough for them to be able to converge the light onto the retina. So the lens is not sufficiently convex. In other words, it's not powerful enough to focus the image. Okay, now the correction for this, incidentally, I've just remembered that I didn't define power at the beginning of the lesson. So that was unfortunate. I meant to do that. I'll have to go back and sort that out. Okay, so how do we fix this? Well, can you see what the solution is going to be? If you want to focus on an object close to the eye and your eye lens is just not powerful enough anymore, it can't quite do the job. So what do you need? Well, what you need is a bit of help. So if we put in another convex lens, then the two convex lenses together will be able to converge the light enough to produce a focused image on the retina. And that's exactly what happens. Now, actually, I am going to do quite diagram 7 in this case, just to show how we get to that. So, in this case, if the object is at the normal near point, we don't get an image. So what can the eye actually do? Well, what you have to do is you have to push the object out. If you push the object out, then the image will move in. And you'll get to a point, which might be, say, out about here, where the eye is able, without correction, to focus the image. So what this means basically is that you move your newspaper further away from your eye. And if you do that, you may be able to reach a point where you can see a focused image. And that's what, older people do. They move things away so that they can focus on it. And that works up to a point until you run out of arms. So in this case, we have to move the object away and put the object at an actual near point, which is greater than 25 centimeters, maybe way out. And then we can obtain a focused image. Now, the point is that that's what the eye can actually deal with. So it can't deal with an object at the normal near point, but it can deal with an object at the actual near point, which might be, say, 75 centimeters or 125 centimeters, something like that. So what we want to do is put in a converging lens that will help. So here's a converging lens. Now what we want is that rays that are coming from an object at the normal near point, that is your newspaper held at a normal distance in front of you. I'm going to put an axis in here to help me. So that rays from that object are going to end up on the retina. I'm drawing the diagram backwards here. Now, what the eye lens can actually focus rays coming from the actual near point, which is here. So if the converging lens converges the rays just a little bit so that they appear to be coming from the actual far point, the actual near point, there, then it can deal with them, like so. Okay, but the rays aren't actually coming from that point. They're actually coming from the object at the desired normal near point, like so. So this is what the lens does. It converges the rays ever so slightly so that they appear to be coming from the actual near point. And then the eye lens says, okay, I can deal with those, and focuses them on the retina. So we have the object at the normal near point. And this is the actual near point. Okay. So what we're saying then is that to correct long sight, the eye lens needs a bit of help. From another converging lens. Okay. So the object is here. The lens converges the light a bit so that it appears to come from the eye's actual near point, and then the eye can finish the job and focus the image on the retina. So what's going on then is that as far as the lens is concerned, the object is at the normal near point, which we want to be at 25 centimeters. Rays from that object are converged slightly so that they appear to come from the actual near point of the eye. Okay. Right, that's all we'll say for that, I think, at this point. Okay, so let's just review. So hypermetropia is long sight. Hyper means long. Long sight means you can focus distant objects, but cannot focus nearby objects. So the problem is nearby things, like reading. So what's the problem? The problem is that if an object is nearby, and in particular if it's at the normal near point, where a normal eye would be able to focus it, then the hypermetropic eye can't focus it. The lens is just not able to focus the rays on the retina. The focus point, the image would be beyond the retina, therefore the image that's obtained is blurred. And this is often, so one cause can be age. So this can be an age-related condition because the eyeball has, or the lens has become stiff with age and can't be made sufficiently convex. Okay, so what happens then is that the object has to be pushed out, and the actual near point will be much further than 25 centimeters. So some greater distance away from the eye lens can actually cope and focus an image on the retina. So the correction for that is that the eye needs a bit of help from a converging lens, and it can do that then by putting a converging lens or a contact lens, which has a converging action, in front of the eyeball. And in that case, the rays are a little bit converged before they reach the eye, so that they actually reach a focus on the retina. And in fact, what we want to do is we want to converge the rays so that they appear to be coming from the person's actual near point, and then the eye lens can deal with them. So therefore the focal length is going to have to be chosen so that if we have an object at a normal near point, the rays are converged so that they appear to come from the actual near point. And when we come to calculations, we'll use that fact. Okay, I'm going to pause at that point. I've gone 36 minutes on that, so this is quite time consuming. I hope you're still with me. I said this was difficult. You might be consuming this in bite-sized chunks, in which case well and good. What you should have now then is 2 sets of diagrams, actually 3, one for the normal eye, one for myopia, and one for hypermetropia. So the next step will be calculations, which we'll do in the next video.